Imagine if you could simply float upward and never come back down. Picture stepping off a cliff and drifting gently into the sky instead of plummeting towards certain death. Envision watching your morning coffee hover mysteriously above your cup, defying every expectation you've ever had about how the world works. This isn't science fiction. This is what would happen if gravity, the invisible force that governs every moment of our existence, suddenly vanished from the universe. What would actually happen if gravity disappeared? The answer is both more immediate and more catastrophic than most people realize. Within seconds, our planet would begin tearing itself apart. Within minutes, the atmosphere would start bleeding into space. Within hours, the Earth itself would begin to disintegrate. And that's just the beginning of a cosmic catastrophe that would unravel the very fabric of reality as we know it. To understand the true horror of a universe without gravity, we need to start with the most fundamental question. What exactly is gravity? And why is it so essential to everything we see around us? Gravity isn't just a force that keeps your feet on the ground. It's the cosmic glue that holds together everything from the smallest pebble to the largest galaxy. Without it, the universe would be a very different place indeed. In fact, without gravity, there would be no universe at all, at least not one that could support the complex structures we see today. The story of gravity begins with Albert Einstein, who revolutionized our understanding of this fundamental force in the early 20th century. Before Einstein, scientists thought of gravity as a simple, attractive force between objects with mass. The more massive something was, the stronger its gravitational pull. This seemed to explain why apples fall from trees and why the moon orbits the Earth. But Einstein revealed something far more profound. Gravity isn't really a force at all. Instead, it's the curvature of space and time itself. Imagine a stretched rubber sheet with a bowling ball placed in the center. The ball creates a depression, and if you roll a marble nearby, it will curve around the depression rather than traveling in a straight line. This is essentially how gravity works. Massive objects like stars and planets warp the fabric of space-time, and other objects follow the curves created by this warping. This understanding becomes crucial when we consider what would happen if gravity simply stopped working. We're not just talking about objects floating away, we're talking about the fundamental geometry of space-time itself becoming flat and featureless. The immediate effects would be spectacular and terrifying. Every person, animal, plant, car, building, and grain of sand on Earth would instantly become weightless. But this isn't the gentle weightlessness that astronauts experience in orbit. Those astronauts are actually in constant freefall, held in a delicate balance between their forward momentum and Earth's gravitational pull. If gravity disappeared, there would be no such balance. Instead, everything would begin moving in perfectly straight lines at whatever velocity they happened to have at the moment gravity vanished. A person walking north at 3 miles per hour would continue drifting north at 3 miles per hour forever, unless they encountered some obstacle. A car travelling down the highway would sail off the road in a straight line, its passengers floating helplessly inside as the vehicle continued its trajectory into space. But the real chaos would come from the Earth's rotation. Our planet spins at roughly 1,000 miles per hour at the equator. Without gravity to hold everything down, this rotational velocity would fling objects tangentially away from the surface. The closer you were to the equator, the faster you'd be launched into space. Those at the poles might drift away more gently, but drift away they would. The atmosphere would be among the first casualties. The air we breathe is held close to Earth's surface by gravitational attraction. Without this force, the entire atmosphere would begin expanding outward into space like an enormous, invisible explosion. The process wouldn't be instantaneous, but it would be irreversible. Within hours, the air would become too thin to breathe. Within days, most of it would be gone entirely. Water would follow a similar fate. The oceans, rivers, and lakes that cover our planet exist as liquid bodies because gravity pulls the water molecules together and down toward the Earth's center. Without this force, water would begin to boil and vaporize much more readily, since there would be no atmospheric pressure to keep it in liquid form. The vast oceans would turn into expanding clouds of water vapor, drifting away into the void. But even these dramatic changes pale in comparison to what would happen to the Earth itself. Our planet isn't just a solid rock floating in space. It's a complex layered structure held together by immense gravitational forces. The core, mantle, and crust exist in their current configuration because gravity pulls everything toward the center with tremendous force. Without gravity, there would be nothing to hold the Earth together. The planet would begin to come apart like a loosely packed snowball in a hurricane. The process would start slowly, with surface materials beginning to drift away, but it would accelerate rapidly. Chunks of rock, mountains, and eventually entire continents would break free and tumble into space. The Earth's molten core, currently kept under tremendous pressure by the weight of everything above it, would begin to expand and cool. Without gravitational compression, the intense heat and pressure that keep the core molten would dissipate. This would shut down the planet's magnetic field, which is generated by the movement of molten metals in the core. Without this magnetic shield, the Earth would be bombarded by deadly cosmic radiation and solar wind. Meanwhile, the Moon would go sailing off into space in a straight line, no longer held in orbit by Earth's gravitational pull. The same would happen to every artificial satellite, the International Space Station, and anything else currently orbiting our planet. They would all continue moving in whatever direction they were traveling when gravity disappeared, becoming lone wanderers in the solar system. The effects would cascade throughout the entire solar system. The planets would break free from their orbits around the Sun and drift away into interstellar space. Mars would head off in one direction, Venus in another, Jupiter in yet another. The asteroid belt would disperse like cosmic confetti, with each rock following its own trajectory through the void. The Sun itself would face its own catastrophic fate. Our star is essentially a massive ball of hydrogen and helium held together by its own gravitational pull. The immense pressure created by this gravitational compression is what allows nuclear fusion to occur in the Sun's core, generating the heat and light that make life on Earth possible. Without gravity, the Sun would begin to expand and cool rapidly. The nuclear fusion reactions would slow down and eventually stop entirely as the stellar material spread out into space. What was once a brilliant, life-giving star would become a vast, cold cloud of gas, gradually dispersing across light years of space. This pattern would repeat throughout the universe. Every star, from the smallest red dwarf to the largest supergiant, would begin to come apart. Galaxies, those magnificent spiral and elliptical collections of billions of stars, would dissolve as their constituent stars drifted away from each other in straight lines. Black holes, those mysterious objects whose gravitational pull is so strong that not even light can escape, would cease to exist. They are defined entirely by their gravitational effects, so without gravity, they would simply become dispersed clouds of matter, spreading outward at incredible speeds. The cosmic web, that vast network of dark matter filaments that connects galaxies across billions of light years, would vanish. Dark matter, which makes up roughly 27% of the universe, interacts primarily through gravitational force. Without gravity, this invisible scaffolding that shapes the large-scale structure of the cosmos would become meaningless. But perhaps the most profound change would be to the nature of time itself. Einstein showed us that gravity and time are intimately connected. Strong gravitational fields actually slow down the passage of time relative to weaker fields. This effect, called gravitational time dilation, has been measured and verified countless times. Without gravity, time would no longer vary from place to place in the universe. A clock on what used to be Earth's surface would tick at exactly the same rate as a clock near what used to be the Sun. This might seem like a minor detail, but it represents a fundamental change in the structure of reality itself. The absence of gravity would also eliminate one of the most important processes in the universe, the formation of complex structures. Gravity is what allows small irregularities in the distribution of matter to grow over time. A region that starts out slightly denser than its surroundings will gravitationally attract more matter, becoming even denser, which allows it to attract still more matter, and so on. This is how stars form from clouds of gas and dust, how planets coalesce from debris around young stars, and how galaxies grow from tiny fluctuations in the early universe. Without gravity, none of these processes could occur. The universe would remain forever a thin, uniform soup of particles, never developing the rich complexity we see today. Life as we know it would be utterly impossible in a universe without gravity. Not just because living beings need a stable environment with liquid water and breathable atmosphere, but because the very atoms that make up living things rely on gravitational processes for their existence. The heavy elements that are essential for life, such as carbon, oxygen, and iron, are forged in the nuclear furnaces at the hearts of stars. These fusion reactions only occur because gravity compresses stellar cores to incredible densities and temperatures. Without gravity, there would be no stars, no fusion reactions, and no heavy elements. The universe would contain only the lightest elements, hydrogen and helium, forever prevented from combining into more complex forms. Even the formation of planets, which provide stable platforms for life to develop, depends entirely on gravitational attraction. Tiny particles of dust and ice in space gradually stick together through electrostatic forces, but it's gravity that allows these small clumps to grow into larger and larger bodies, eventually becoming asteroids, moons, and planets. The disappearance of gravity would also have strange effects on the fundamental forces of nature. While gravity is by far the weakest of the four fundamental forces under normal circumstances, it becomes dominant on large scales, because it's always attractive and because it acts over infinite distances. The electromagnetic force, which governs the behavior of atoms and molecules, would suddenly become the primary force shaping the universe. But electromagnetic forces can be both attractive and repulsive, and they tend to cancel out over large distances. Without gravity to provide an overall attractive influence, matter would be governed entirely by the complex interplay of electromagnetic forces. This would create a very different kind of universe. Instead of the smooth, large-scale structures we see today, space might be filled with complex electromagnetic patterns and fields. Charged particles would spiral along magnetic field lines, creating intricate geometries that bear no resemblance to the galaxies and star clusters we're familiar with. The strong nuclear force which holds atomic nuclei together would continue to operate normally, but without gravity to create the extreme conditions necessary for nuclear fusion, atomic nuclei would remain simple. The universe would be stuck with the basic building blocks of matter, unable to forge them into more complex forms. The weak nuclear force, responsible for certain types of radioactive decay, would also continue unchanged. But many of the processes that depend on this force, such as the nuclear reactions that power stars, would never get started without gravity to create the necessary conditions. In essence, a universe without gravity would be a universe frozen in simplicity. The rich tapestry of cosmic evolution, from the first stars to the emergence of life, depends on gravity's ability to gather matter together and create the extreme conditions necessary for complex processes to occur. But what if gravity didn't disappear all at once? What if it gradually weakened over time? the effects would be no less catastrophic, just slower to unfold. As gravitational attraction decreased, the orbits of planets would gradually expand. Earth would slowly spiral away from the Sun, receiving less and less heat and light. The planet's surface would begin to cool as we move farther from our life-giving star. The polar ice caps would expand, eventually covering most of the planet in ice. The atmosphere would start to thin as the weakening gravity gradually lost its grip on the air molecules. Meanwhile, the Sun itself would begin to expand as its weakening self-gravity could no longer contain its outer layers as effectively. The star would become cooler and redder, hastening the Earth's descent into a frozen wasteland. Tides, which are caused by the gravitational pull of the Moon and Sun on Earth's oceans, would become weaker and eventually disappear entirely. This might seem like a minor change, but tides play a crucial role in ocean circulation and marine ecosystems. Their absence would have far-reaching effects on life in the oceans. The gradual weakening of gravity would also affect the Earth's internal structure. The planet's core would slowly expand and cool as the pressure from above decreased. This would weaken the magnetic field that protects us from cosmic radiation, making the surface increasingly hostile to life. Even human physiology would be affected by gradually weakening gravity. Our bodies have evolved under Earth's gravitational influence, and our bones, muscles, and cardiovascular systems all depend on gravity to function properly. Astronauts who spend extended periods in low gravity experience bone loss, muscle atrophy, and cardiovascular deconditioning. In a world of gradually weakening gravity, humans would need to adapt to an environment where they became progressively lighter and more fragile. Buildings and infrastructure designed for normal gravity would become unstable and dangerous as the force holding them together weakened. The complete absence of gravity would represent one of the most fundamental changes possible to the nature of reality. It would be like removing one of the basic rules that govern how the universe operates. The result would be chaos on a cosmic scale, followed by a strange, simplified universe, utterly unlike anything we can imagine. Yet for all its catastrophic effects, the disappearance of gravity would also reveal the true elegance and interconnectedness of the cosmos. Every aspect of the universe we know, from the largest galaxy to the smallest atom, has been shaped by gravitational forces. Remove this single influence, and the entire cosmic story changes beyond recognition. This thought experiment highlights just how precisely balanced and interconnected our universe really is. Gravity may seem like a simple, obvious force, but it's actually the foundation upon which all cosmic complexity rests. Without it, we would have no stars, no planets, no life, and no observers to contemplate the strange, empty universe that would remain. Now, if gravity suddenly disappeared from the universe, the consequences would extend far beyond what we initially explored. The immediate catastrophe of floating objects and escaping atmospheres would be just the beginning of a cosmic transformation that reaches into the very foundations of matter itself. Within the first few seconds after gravity's disappearance, we would witness something extraordinary happening at the atomic level. The nuclei of atoms, which house protons and neutrons bound together by the strong nuclear force, would begin to experience unprecedented changes. While gravity doesn't directly hold atomic nuclei together, its absence would trigger a cascade of effects that fundamentally alter how matter behaves throughout the universe. The strong nuclear force, which binds protons and neutrons within atomic nuclei, operates over incredibly short distances. Under normal circumstances, gravity provides a subtle but important background influence that helps maintain the delicate balance of forces within stellar cores, where nuclear fusion occurs. Without gravity's compressive effects, the nuclear processes that forge heavier elements would cease immediately. Every star in the universe would instantly stop fusing hydrogen into helium, and the more massive stars, that create carbon, oxygen, and iron would halt their element-building factories forever. But the implications go deeper still. The quantum mechanical processes that govern how particles interact depend on the overall energy landscape of the universe. Gravity, though the weakest of the four fundamental forces, contributes to this landscape in ways that modern physics is only beginning to understand. Without gravitational potential energy, the quantum vacuum itself would shift into a different state, potentially altering the behavior of virtual particles that constantly pop into and out of existence. This quantum shift would have profound consequences for the electromagnetic force that holds electrons in orbit around atomic nuclei. While atoms wouldn't immediately disintegrate, their electronic structures would begin to drift and change as the universal energy balance shifts. Over time, this could lead to new forms of chemistry that have never existed before, with electrons occupying different orbital configurations and atoms forming bonds in previously impossible ways. The weak nuclear force, responsible for certain types of radioactive decay, would also be affected. The delicate balance between the four fundamental forces that has remained stable for over 13 billion years would be shattered. Without gravity's influence, the decay rates of radioactive elements would change, potentially accelerating or slowing depending on the specific isotope. This would have immediate consequences for any technology that relies on nuclear processes, from medical imaging equipment to nuclear power plants. Perhaps most remarkably, the absence of gravity would reveal just how interconnected the fundamental forces truly are. Modern physics suggests that at extremely high energies, all four forces merge into a single unified force. While we can't recreate those conditions in laboratories, the sudden removal of gravity would provide the universe with a natural experiment in fundamental physics. The remaining three forces might begin to behave differently, potentially even attempting to compensate for gravity's absence by strengthening their own interactions. This compensation effect could manifest in several ways. The electromagnetic force might become slightly stronger, causing atoms to bind more tightly together and making chemical reactions more energetic. The strong nuclear force could extend its reach slightly beyond atomic nuclei, creating new types of exotic matter that exist only in a gravity-free universe. The weak force might accelerate its decay processes, causing normally stable particles to become radioactive. These changes would transform the very nature of matter itself. In our current universe, the precise strengths of the fundamental forces allow for the existence of stable atoms, complex molecules, and ultimately life. But in a gravity-free cosmos, new forms of matter would emerge. We might see the formation of ultra-dense electron clouds that exist independently of atomic nuclei, or witness the creation of exotic particles that can only exist when gravity's constraining influence is removed. The quantum field that gives particles their mass, known as the Higgs field, would also be affected. This field permeates all of space and interacts with particles to give them their characteristic masses. Without gravity's contribution to the overall energy density of the universe, the Higgs field might shift to a different energy state, potentially changing the masses of fundamental particles like electrons, quarks, and neutrinos. If particle masses began to change, the consequences would be immediate and dramatic. Electrons might become heavier or lighter, altering the sizes of atoms and the strengths of chemical bonds. Quarks could shift their masses, changing the binding energy of protons and neutrons and making atomic nuclei either more or less stable. Even neutrinos, which barely interact with ordinary matter, could see their masses altered in ways that change how they travel through the cosmos. This mass transformation would create a universe where the periodic table itself becomes fluid and changeable. Elements that are stable today might become radioactive, while currently unstable isotopes could achieve new forms of stability. The chemistry that makes life possible would be rewritten from the ground up, potentially making carbon-based life impossible, while opening the door to entirely new forms of matter-based complexity. As these fundamental changes ripple through the cosmos over the course of minutes and hours, after gravity's disappearance, we would witness the emergence of a truly alien universe. The familiar matter that makes up planets, stars, and living beings would begin transforming into exotic new forms that have never existed in our gravitational cosmos. The universe wouldn't simply become empty and dark, it would become a laboratory for entirely new physics, where the remaining three fundamental forces explore possibilities that gravity has suppressed for nearly 14 billion years. This transformation represents perhaps the most profound change imaginable, not just the destruction of the universe as we know it, but its rebirth into something completely unprecedented in the history of physics itself. As we embark on this next chapter of our cosmic journey, we find ourselves standing at the threshold of an era that would fundamentally transform the universe from a dark, formless void into the magnificent tapestry of stars, galaxies, and cosmic structures we observe today. The stage has been meticulously set by the preceding billion years of cosmic evolution, yet what unfolds next represents perhaps the most dramatic transformation in the entire history of the universe. Picture, if you will, the cosmos as it existed roughly 1 billion years after the Big Bang. It was a universe caught in perpetual twilight, filled with the invisible scaffolding of dark matter that had been quietly weaving itself into vast cosmic webs spanning millions of light years. Hidden within this darkness lay pockets of primordial gas, predominantly hydrogen and helium, slowly cooling and condensing under the relentless pull of gravity. These were the cosmic nurseries, where the first stars would soon ignite, bringing light to a universe that had known only darkness for hundreds of millions of years. The transition from this cosmic dark age to the epoch of stellar birth was not a gentle awakening, but rather a violent and spectacular revolution. As the first massive clouds of gas reached critical densities, they began to collapse under their own weight with increasing velocity. The temperature at their cores climbed steadily, and when it finally reached 10 million degrees Celsius, something extraordinary happened. Nuclear fusion ignited for the first time since the Big Bang itself, and the universe's first stars blazed into existence. These primordial giants were unlike anything we see in the modern cosmos. Born from pure hydrogen and helium, with virtually no heavier elements to speak of, they were massive beyond imagination, some reaching hundreds of times the mass of our Sun. They burned with an intensity that defies comprehension, their surfaces reaching temperatures of 50,000 degrees or more, making them appear brilliant blue-white beacons against the cosmic darkness. Yet for all their magnificence, these stellar titans were destined for brief explosive lives. The nuclear furnaces at the hearts of these first stars worked with unprecedented fury, fusing hydrogen into helium, then helium into carbon, oxygen, neon, and silicon in an ascending ladder of nuclear alchemy. Each successive fusion reaction required higher temperatures and pressures, pushing these stellar cores to ever more extreme conditions. Within just a few million years, a mere instant in cosmic terms, they had exhausted their nuclear fuel and faced an inevitable and catastrophic end. What happened next changed the very chemistry of the universe forever. Unable to support themselves against their own crushing gravity, these massive stars collapsed in upon themselves before exploding outward in the most violent events the young universe had ever witnessed. These first supernovae released more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime, sending shockwaves rippling through space at thousands of kilometers per second and illuminating regions of the cosmos spanning hundreds of light years. But perhaps even more significant than their spectacular deaths was what these stellar explosions left behind. During their brief lives and violent deaths, the first stars had forged virtually every element heavier than hydrogen and helium that would ever exist in the universe. Carbon, the foundation of all organic chemistry. Oxygen, essential for water and complex molecules. Iron, which would one day flow through the veins of living creatures. Gold, silver, and platinum, elements so precious they could only be created in the most extreme nuclear furnaces imaginable. These newly minted elements, scattered across vast regions of space by the explosive force of supernovae, began to mix with the primordial hydrogen and helium gas clouds. This cosmic enrichment process was gradual but inexorable, and when the next generation of stars formed from this chemically enhanced material, they were fundamentally different from their predecessors. They were smaller, longer-lived, and capable of hosting the rocky planets that would eventually become the cradles of life. The transformation of the universe during this epoch extended far beyond the birth and death of individual stars. As more and more stellar furnaces ignited across the cosmos, they began to fundamentally alter the very nature of space itself. The intense radiation and stellar winds from these early stars heated and ionized the surrounding gas, creating vast bubbles of hot plasma that expanded outward like cosmic balloons. This process, known as reionization, gradually transformed the universe from a collection of cold, neutral atoms back into a plasma state, though now one that was far more diffuse and structured than the opaque soup that had existed immediately after the Big Bang. The cumulative effect of countless stellar births and deaths was to carve out ever larger regions of ionized space, creating a cosmic Swiss cheese of hot bubbles separated by cooler, denser filaments of dark matter and gas. These filaments served as highways along which matter could flow, feeding the formation of ever larger structures. What had begun as tiny quantum fluctuations in the earliest moments after the Big Bang had now grown, through the inexorable action of gravity and the transformative power of stellar nucleosynthesis, into the first recognizable galaxies. These primordial galaxies were chaotic, violent places, bearing little resemblance to the majestic spiral and elliptical galaxies we observe in the modern universe. They were smaller, more irregular, and engaged in a constant process of collision and merger as they swept up surrounding material and absorbed their smaller neighbours. The rate of star formation within these early galactic structures was prodigious, sometimes hundreds of times greater than what we observe in contemporary galaxies, leading to a cosmic baby boom that populated the universe with stellar light for the first time in its history. As this epoch of cosmic awakening progressed, the universe began to develop the hierarchical structure that characterizes it today. The largest dark matter halos became the sites of the most massive galaxies, which in turn became the centers of even larger structures as they gravitationally attracted their smaller neighbors. The cosmic web of dark matter that had been invisible for so long now became outlined in brilliant starlight as gas flowed along its filaments and pooled in its densest nodes. Yet even as this grand architecture of cosmic structure took shape, profound mysteries remained. The process by which the first stars formed from pristine primordial gas was incredibly complex and sensitive to countless variables. The precise mass and temperature of collapsing gas clouds, the strength of magnetic fields, the rate of cooling through radiation, and the complex feedback effects of stellar radiation and supernova all played crucial roles in determining when, where, and how efficiently stars could form. Perhaps most remarkably, this entire transformation occurred through the action of physical processes that we can observe and study in laboratories here on Earth. The nuclear fusion reactions that powered the first stars operate according to the same quantum mechanical principles that govern atomic interactions in our modern world. The gravitational collapse that triggered star formation follows the same mathematical laws that Newton and Einstein discovered centuries later. The chemical elements forged in stellar cores and dispersed by supernova are the very same atoms that make up our bodies and our planet. As we conclude this phase of our cosmic journey, we find ourselves witnesses to one of the most profound transformations in the history of the universe. In the span of just a few 100 million years, the cosmos had evolved from a dark, cold, and chemically simple state to a brilliant, complex, and chemically rich tapestry of stellar light and galactic structure. The universe had learned to shine, and in doing so, had set the stage for all the wonders that would follow, from the formation of planets and the emergence of life, to the eventual appearance of conscious beings capable of contemplating their own cosmic origins. Without gravity, the universe would undergo a catastrophic unraveling that touches every aspect of cosmic existence, from the grandest galactic structures down to the fundamental forces that bind matter itself. The immediate aftermath would be nothing short of apocalyptic. Earth's atmosphere, currently held in place by our planet's gravitational embrace, would instantly begin its exodus into space. The air we breathe, the protective blanket that shields us from cosmic radiation, would simply drift away like smoke in a cosmic wind. Within minutes, the breathable atmosphere would thin to lethal levels, while the oceans would follow suit, their waters boiling away into the vacuum as atmospheric pressure plummeted. But Earth's atmospheric escape would be merely the opening act in a far grander cosmic tragedy. Our planet itself, no longer bound to the sun's gravitational influence, would begin its lonely journey into the interstellar void. The entire solar system would disintegrate as the planets, asteroids, and comets that have danced in gravitational harmony for over 4 billion years suddenly found themselves free from their celestial choreography. The sun, that nuclear furnace at the heart of our solar system, would face its own existential crisis. Without gravity to compress its core and maintain the intense pressures necessary for nuclear fusion, the delicate balance between gravitational collapse and outward radiation pressure would shatter. The star would begin to expand uncontrollably, its nuclear fires gradually dimming as the core temperature dropped below the threshold needed to fuse hydrogen into helium. What was once a brilliant beacon of light and energy would transform into a cold, expanding cloud of gas, dispersing its constituent atoms across the cosmos. This stellar death would be replicated countless times throughout the universe. Every star, from the smallest red dwarf to the most massive supergiant, would suffer the same fate. The night sky, once alive with the light of billions of stars, would gradually darken as these cosmic furnaces extinguished themselves, one by one. The very process that has illuminated the universe for nearly 14 billion years would grind to a halt. Galaxies themselves, those magnificent spiral and elliptical collections of hundreds of billions of stars, would begin to unravel. The Milky Way, our cosmic home, would lose its characteristic spiral structure as stars drifted away from their orbital paths. The supermassive black hole at the galactic center, no longer able to exert its gravitational influence, would become just another object floating freely through space. Galaxy clusters, the largest gravitationally bound structures in the universe, would dissolve as their constituent galaxies scattered like dandelion seeds on a cosmic breeze. Perhaps most dramatically, black holes themselves would cease to exist. These cosmic monsters, whose gravitational pull is so intense that not even light can escape, are fundamentally defined by their warping of space-time. Without gravity, the very concept of a black hole becomes meaningless. The event horizons that mark the point of no return would simply vanish, and any matter previously trapped within would be released back into the universe. The cosmic web, that magnificent, large-scale structure of the universe composed of dark matter filaments connecting galaxy clusters across billions of light-years, would collapse entirely. Dark matter, which comprises approximately 27% of the universe, and whose presence is inferred primarily through its gravitational effects, would lose its primary means of interaction with the cosmos. These invisible scaffolds that have guided the formation of galaxies and large-scale structure would no longer be able to clump together or influence the distribution of normal matter. But the consequences extend far beyond the immediate structural collapse of cosmic architecture. Gravity plays a fundamental role in the very physics that govern our universe, and its absence would trigger a cascade of effects that reach down to the quantum level. The formation of new stars would become impossible. Starbirth requires the gravitational collapse of giant molecular clouds, where gas and dust condense under their own weight, until temperatures and pressures become sufficient to ignite nuclear fusion. Without gravity to compress these stellar nurseries, the universe would be left with only the stars that already exist, each slowly dying as they exhaust their nuclear fuel, with no possibility of replacement. The synthesis of heavy elements, which occurs in the hearts of massive stars and during supernova explosions, would cease entirely. Throughout cosmic history, successive generations of stars have forged the elements heavier than hydrogen and helium through nuclear fusion, enriching the interstellar medium with the carbon, oxygen, silicon, and iron that form the building blocks of planets and life itself. This cosmic recycling program, driven by gravitational collapse and stellar evolution, would come to an abrupt end. Time itself would behave differently in a universe without gravity. Einstein's general relativity reveals that gravity and time are intimately connected through the curvature of space-time. Massive objects create gravitational wells that slow the passage of time relative to regions of weaker gravitational influence. Without gravity, space-time would become completely flat, and time would flow uniformly throughout the universe. The subtle time dilations that we observe near massive objects, from the GPS satellites orbiting Earth to the extreme warping near black holes, would disappear entirely. The fundamental nature of space would also transform. Currently, the presence of matter and energy curves the fabric of space-time, creating the gravitational effects we observe. In a universe without gravity, space-time would become perfectly flat and static, resembling the idealized geometry of Euclidean space, rather than the dynamic, curved manifold described by general relativity. Even the expansion of the universe itself would be affected. While cosmic expansion is driven primarily by dark energy rather than gravity, gravitational attraction has historically played a crucial role in slowing this expansion and allowing structure formation. The delicate balance between the outward push of dark energy and the inward pull of gravity has shaped the cosmic timeline, determining when and how galaxies could form. Without gravity's restraining influence, the expansion might proceed differently, though the universe would already be facing far more immediate catastrophes. The implications for life would be absolute and immediate. Life as we know it depends not only on the gravitational stability of planetary systems, but also on the ongoing stellar processes that provide energy and create the chemical elements necessary for biological complexity. Without gravity, there would be no stable planets orbiting life-giving stars, no geological processes to recycle nutrients and regulate planetary climates, and no stellar nuclear synthesis to create the diverse chemical palette that life requires. Perhaps most profoundly, the very concept of cosmic evolution would become meaningless. The universe's 14 billion year journey from a hot, dense state to the rich tapestry of structure we observe today has been fundamentally shaped by gravity's ability to amplify tiny density fluctuations into vast cosmic structures. The cosmic microwave background radiation preserves the imprint of these primordial fluctuations, showing us how gravity took the quantum uncertainties of the early universe and transformed them into the seeds of galaxies and galaxy clusters. In a universe without gravity, these density fluctuations would remain forever frozen at their initial amplitude. There would be no mechanism to build complexity, no way for simple hydrogen and helium to evolve into the rich chemical diversity we observe, and no process to concentrate matter into the dense environments necessary for stellar ignition. The universe would remain essentially unchanged from its initial state, a gradually cooling and expanding soup of elementary particles and radiation. The absence of gravity would represent not just the end of cosmic structure, but the end of cosmic potential itself. Every star that will ever shine, every planet that could ever form, every possibility for complexity and consciousness would be eliminated in an instant. The universe would become a place of ultimate simplicity and ultimate emptiness, where the only motion would be the relentless expansion, carrying particles ever further apart into an increasingly cold and lonely cosmic void. This thought experiment reveals gravity not as merely one force among four, but as the architect of cosmic complexity and the guardian of structure itself. Without gravity's patient work over cosmic time, shaping matter into ever more intricate configurations, the universe would be reduced to its most fundamental and featureless state, a vast expanse of space containing nothing more than isolated particles drifting eternally apart, with no possibility of reunion, no chance for complexity, and no hope for the emergence of anything resembling the rich structured cosmos we call home. Part 5. The collapse of everything. Imagine for a moment what happens when the very force that holds our universe together suddenly vanishes. We've explored how gravity shapes cosmic structures, enables stellar fusion, and allows complexity to emerge from chaos. But what if this fundamental force simply disappeared? What would become of the intricate cosmic web, the blazing stars, and the delicate dance of planets around their suns? The answer is both immediate and catastrophic. Without gravity, every structure in the universe would begin to disintegrate in a cascade of cosmic destruction that would unfold across multiple scales simultaneously. Let's start with the most familiar scale, our own solar system. The moment gravity disappears, Earth would no longer follow its orbital path around the Sun. Instead, our planet would shoot off into space in a straight line at approximately 30 kilometers per second, carrying with it whatever remains of our atmosphere and oceans. But even this assumes Earth would remain intact, which it wouldn't. You see, gravity is what holds our planet together in the first place. The rocky mantle, the metallic core, the vast oceans, and the thin shell of atmosphere we breathe. All of these are bound to Earth by gravitational attraction. Without this force, the planet would literally fall apart. The atmosphere would expand into space within minutes, the oceans would boil away into the vacuum, and the solid Earth itself would gradually disperse as its constituent rocks, minerals, and particles drift apart. But Earth's destruction would be a minor footnote compared to what happens to the Sun. Our star is a delicate balance between the inward pull of gravity trying to collapse it and the outward pressure of nuclear fusion trying to blow it apart. Remove gravity from this equation and the Sun becomes a massive nuclear explosion, expanding at thousands of kilometers per second. The stellar material that has been compressed to extraordinary densities in the solar core would suddenly have nothing holding it together. The result would be a blast that makes the most powerful supernova look gentle by comparison. This same fate would befall every star in the galaxy simultaneously. Imagine billions upon billions of stars suddenly exploding at once, not because they've reached the end of their natural lives, but because the force that gave them structure has vanished. The night sky would become a blazing inferno of expanding stellar debris. though of course there would be no one left to witness this cosmic fireworks display. On larger scales, the destruction becomes even more profound. Galaxies, those majestic spiral and elliptical collections of hundreds of billions of stars, exist only because gravity binds them together. Without this force, every galaxy would dissolve into its component stars, which would then explode as we've described. But it goes deeper than that. The supermassive black holes that sit at the centres of most galaxies containing millions or billions of times the mass of our Sun would also cease to exist. Now you might think that black holes, being regions where gravity is so strong that not even light can escape, would be immune to gravity's disappearance. But you'd be wrong. Black holes are not objects in the traditional sense. They are manifestations of extremely curved space-time, and space-time curvature is gravity. Remove gravity, and black holes simply vanish, releasing all the matter and energy they've accumulated over billions of years in an instant. The cosmic web itself, that vast network of dark matter filaments connecting galaxy clusters across billions of light years, would dissolve. Dark matter, whatever it actually is, interacts primarily through gravity. Without this force, the scaffolding upon which all large-scale cosmic structure is built would collapse, leaving behind only expanding clouds of particles with no organization or coherence. But perhaps the most profound consequence would be at the quantum level. We often think of gravity as the weakest of the four fundamental forces, and in many contexts this is true. But gravity plays crucial roles even in atomic nuclei. The strong nuclear force holds protons and neutrons together in atomic nuclei, but gravity contributes to the overall stability of matter in ways we're only beginning to understand. Without gravity, the universe would lose one of its fundamental organizing principles. The elegant hierarchy of structures, from particles to atoms, to molecules, to planets, to stars, to galaxies, exists because gravity provides the scaffolding for complexity to emerge. Remove this scaffolding, and complexity itself becomes impossible. The expansion of space driven by dark energy would continue unabated, but now, instead of a universe filled with galaxies, stars, and planets, all slowly growing apart, we'd have a universe filled with expanding clouds of elementary particles, all moving away from each other at ever-increasing speeds. The temperature would plummet as this expansion continues, and within a relatively short time, perhaps millions of years rather than the trillions gravity would have allowed, the universe would become a cold, dark, empty expanse. Even the formation of new structures would be impossible. Stars form when gravity causes clouds of gas to collapse and heat up until nuclear fusion ignites. Planets form when gravity pulls together dust and rock around young stars. Life emerges on planets where gravity creates stable environments and drives the geological processes that make chemistry complex and interesting. None of this could happen in a universe without gravity. Perhaps most chilling of all, this wouldn't be a gradual decline into emptiness. The destruction would be swift and absolute. Within hours, every organized structure in the universe would be gone. Within days, the expanding debris clouds would be so dispersed that the density of matter would be lower than the best vacuum we can create in our laboratories today. The universe would become a monument to entropy, a vast, expanding emptiness where particles drift apart forever, never again to interact in meaningful ways, never again to build the complex hierarchies of structure that make chemistry, biology, and consciousness possible. It would be a universe where nothing interesting could ever happen again. This thought experiment reveals something profound about the nature of our cosmos. Gravity isn't just one force among many, it's the architect of complexity itself. It's the force that allows the universe to build upward from simple beginnings to create the rich, structured, dynamic cosmos we inhabit. Without gravity, there would be no stars to forge the heavy elements necessary for life. No planets to provide stable environments, no galaxies to organize stellar populations, and no cosmic web to channel matter into the dense regions where structure can form. The universe without gravity would be a universe without possibility, without future, without hope. It would be existence reduced to its most fundamental and boring components, elementary particles drifting apart in an ever-expanding void, carrying no information, building no complexity, creating no beauty. And yet, gravity does exist. The universe does build complex structures. Stars do shine, planets do orbit, galaxies do spiral, and on at least one small world, matter has organized itself into patterns complex enough to contemplate its own existence. The fact that we can even imagine a universe without gravity is itself a testament to gravity's creative power. It's the force that made our brains possible in the first place. Now let's continue our cosmic journey into the era when gravity's absence would spell ultimate doom for the very atoms that make up matter itself. By now, we've witnessed how a universe without gravity would lose its atmospheres, shatter its planets, and see its stars extinguished forever. But the story doesn't end there. The absence of gravity would reach deep into the quantum realm, disrupting processes that we might never have imagined were dependent on this fundamental force. Consider the atoms in your body right now. Each one is a delicate balance of forces. The electromagnetic force binds electrons to nuclei, creating the stable atoms that form molecules, cells, and ultimately you. But gravity plays a subtle yet crucial role in maintaining the very stability of matter itself. In our gravitational universe, the weak nuclear force governs radioactive decay at predictable rates. Carbon-14 decays with a half-life of about 5,730 years, allowing us to date ancient artifacts and fossils. But this process depends on the precise balance of forces that gravity helps maintain. Without gravity's influence on the fabric of space-time itself, the fundamental constants that govern these decay rates would shift dramatically. The fine structure constant, that mysterious number close to 137 that determines the strength of electromagnetic interactions, exists in its current form partly because of how gravity shapes the universe's evolution. Remove gravity, and this constant would fluctuate wildly. Electrons would no longer orbit nuclei in stable configurations. The very concept of an atom as we know it would cease to exist. But perhaps most remarkably, without gravity's role in the early universe, the process that created the matter we're made of would never have occurred. Big Bang nucleosynthesis, the cosmic forge that created hydrogen, helium, and lithium in the universe's first 20 minutes, relied on gravity to compress and heat the primordial plasma to the temperatures needed for nuclear fusion. In those crucial early moments, gravity worked alongside the strong nuclear force to overcome electromagnetic repulsion between protons. This delicate dance allowed the first atomic nuclei to form. Without gravity's compressive influence, the universe would have remained a thin soup of individual protons and neutrons, never achieving the densities and temperatures required for nuclear synthesis. Even more fundamentally, the neutron-to-proton ratio that emerged from those early moments was influenced by gravity's role in the cooling rate of the universe. This ratio determined that our universe would be roughly 75% hydrogen and 25% helium by mass. Change this ratio by removing gravity's influence, and you get a universe that's either all neutrons, which would decay into a sparse collection of protons and electrons, or all protons, which couldn't form the complex nuclei needed for chemistry and life. The quantum vacuum itself, that seething foam of virtual particles that pop in and out of existence, even in empty space, depends on gravity for its stability. Heisenberg's uncertainty principle allows energy to fluctuate, borrowing from the vacuum and paying it back almost instantly. But these fluctuations occur within the curved spacetime that gravity creates. Remove gravity, and the quantum vacuum becomes unstable, leading to catastrophic particle creation that would tear apart any remaining matter. In our gravitational universe, these vacuum fluctuations actually contribute to dark energy, driving the accelerated expansion we observe today. But without gravity to regulate them, these same fluctuations would become runaway processes, creating so much energy that spacetime itself would become unstable. The story extends even to consciousness and information processing. The neurons in your brain fire in patterns that depend on the precise movement of ions across cell membranes. These movements rely on electromagnetic forces operating within gravitationally stable atoms. Without gravity, the very atoms that make up neurotransmitters would be unstable, making complex information processing, and therefore consciousness, impossible. Even the photons carrying information would be affected. In our universe, light travels in straight lines through the curved spacetime that gravity creates. This allows complex structures, like eyes and telescopes, to focus light and create images. Without gravity's influence on spacetime geometry, light would propagate in ways that make focusing impossible, eliminating any possibility of vision or optical information processing. The universe without gravity wouldn't just be a place where planets float apart and stars never form. It would be a realm where the very concept of stable matter breaks down at the most fundamental level. The elegant dance of forces that allows complexity to emerge from simplicity would be replaced by chaos. Atoms would be unstable, molecules impossible, and the intricate chemistry that enables life utterly inconceivable. In such a universe, even the concept of time would be different. Without massive objects to curve spacetime, there would be no gravitational time dilation, no event horizons, no way for different regions of space to experience time at different rates. The rich temporal structure that gravity provides, allowing for the formation of black holes, the evolution of stars, and the expansion of the universe itself, would be replaced by a flat, featureless temporal landscape. This reveals gravity's most profound role. It's not just a force that pulls objects together, it's the architect of complexity itself, the force that allows simple ingredients to combine into ever more intricate structures. From the quantum realm to the cosmic scale, gravity provides the framework within which all other forces can operate, creating the stable, hierarchical universe that gave rise to stars, planets, chemistry, biology, and ultimately, beings capable of contemplating their own existence. Without gravity, the universe wouldn't just be empty, it would be impossible. Looking at the incredible cosmic journey we've explored together, from the quantum foam of the Planck era to the emergence of dark matter's invisible scaffolding, we now arrive at a pivotal moment in our universe's story. The stage has been meticulously set through nearly 1 million years of cosmic evolution, yet our tale is far from over. In fact, we're about to witness one of the most profound transformations in the entire history of existence. You see, everything we've discussed so far, the splitting of fundamental forces, the creation of the first atoms, the mysterious dance of dark matter, has been building toward this moment. Because while the universe may have escaped its opaque infancy and cooled into transparency, it remains shrouded in an entirely different kind of darkness. Not the impenetrable fog of plasma that once trapped light, but the cold, empty darkness of a cosmos waiting to truly come alive. For hundreds of millions of years after the cosmic microwave background was released, the universe entered what cosmologists call the Dark Ages. This wasn't darkness in the sense of evil or foreboding, but rather the absence of the brilliant beacons that would eventually illuminate the cosmic web. No stars yet burned in the void, no galaxies spiraled majestically through space. The universe was filled with nothing but cold, neutral hydrogen and helium gas, slowly collapsing under gravity's patient pull into the dark matter structures we've come to understand. But darkness, as we'll discover, was merely the prelude to the universe's most spectacular awakening, because hidden within those cold clouds of primordial gas were the seeds of cosmic dawn, the raw materials that would ignite into the first stars and transform our universe from a dark, lifeless void into the brilliant, dynamic cosmos we observe today. This transformation wasn't just important, it was absolutely crucial for everything that would follow. Without the events we're about to explore, there would be no heavy elements beyond lithium, no carbon for complex chemistry, no oxygen for water, no iron for the cores of rocky planets, no silicon for the circuits that might one day contemplate their own existence. The entire periodic table as we know it, and with it the very possibility of complexity and life, hung in the balance during this critical epoch. The first stars weren't just balls of burning gas, they were cosmic alchemists, forging the essential ingredients for planets, biology, and consciousness itself. But their story is far more dramatic and consequential than you might imagine. These stellar pioneers lived fast, died young, and in their spectacular deaths seeded the universe with the chemical diversity that makes our existence possible. And here's where our story takes an even more fascinating turn, because while these first stars were busy creating the building blocks of complexity, they were also fundamentally reshaping the very fabric of space itself. They were tearing apart the neutral hydrogen that filled the universe, ionizing it in a process that would literally make the cosmos transparent in an entirely new way. This wasn't just stellar formation, this was cosmic reionization, a universe-wide phase transition that would determine whether future generations of stars and galaxies could form at all. But perhaps most remarkably, the seeds of our own existence were being sown during this epoch. The Milky Way galaxy, the solar system, Earth, and ultimately life itself, all trace their origins back to the chemical enrichment provided by these first stellar generations. In a very real sense, we are the children of cosmic dawn, forged from the ashes of stars that burned and died billions of years before our sun was even a glimmer in a molecular cloud. The transition from the Dark Ages to the Age of Stars represents one of the most profound transformations in cosmic history, a shift from simplicity to complexity, from darkness to light, from a universe of potential to one of spectacular reality. It's the moment when the universe truly began to resemble the magnificent cosmic cathedral we observe today, complete with the intricate architecture of galaxies, the brilliant illumination of stellar furnaces, and the chemical foundation for the emergence of life itself. This cosmic dawn wasn't just an astronomical event, it was the birth of possibility itself. As we transition from the immediate cosmic aftermath into a more stable era, something remarkable begins to unfold. The universe, now roughly 1 million years old, has settled into a rhythm that will define the next several billion years of cosmic evolution. The fundamental forces have found their distinct roles, the basic particles have acquired their characteristic properties, and the stage is set for the grand construction project that will transform a relatively smooth cosmos into the rich, structured universe we observe today. But this transformation will not happen overnight. In fact, we are entering what cosmologists sometimes call the Dark Ages of the universe, a period spanning hundreds of millions of years, when the cosmos was largely devoid of the brilliant light sources that would later illuminate the night sky. The afterglow of creation, that cosmic microwave background radiation, had by now cooled and redshifted into the microwave portion of the electromagnetic spectrum, leaving the universe in relative darkness. Yet this darkness was deceptive. While the universe may have appeared quiet and uneventful to any hypothetical observer, beneath the surface, profound changes were taking place. The slightly uneven distribution of matter that had been imprinted during the cosmic microwave background era was beginning to assert itself through the inexorable pull of gravity. Those tiny fluctuations, mere ripples in the cosmic density field, were about to become the seeds of galaxies, stars, and ultimately, life itself. The key player in this cosmic drama was not the ordinary matter that we see around us today, but rather a mysterious and invisible component that scientists have come to call dark matter. This enigmatic substance, which makes up roughly 85% of all matter in the universe, interacts only weakly with ordinary matter and electromagnetic radiation, making it effectively invisible to our telescopes and instruments. Yet its gravitational influence is profound and far-reaching. As the universe continued to expand and cool, dark matter began to clump together under its own gravitational attraction. Unlike ordinary matter, which was still too hot and energetic to form stable structures, dark matter could begin the process of gravitational collapse much earlier in cosmic history. These dark matter clumps acted like gravitational scaffolding, creating deep potential wells into which ordinary matter would eventually fall. The process was gradual but relentless. Over millions of years, dark matter particles drifted toward regions of slightly higher density, making those regions even denser and therefore more gravitationally attractive. This created a positive feedback loop. More matter attracted more matter, which attracted even more matter. What had started as tiny variations in density grew into substantial concentrations of mass. As this dark matter scaffolding took shape, it began to form a complex web-like structure that would come to define the large-scale architecture of the universe. Dense nodes of dark matter, destined to become the cores of galaxy clusters, were connected by elongated filaments stretching across hundreds of millions of light-years. Between these filaments lay vast voids, regions where matter was sparse and would remain so for billions of years to come. Meanwhile, ordinary matter, the protons, neutrons, and electrons that would eventually form stars, planets, and people, was following a somewhat different trajectory. Still hot from the energetic processes of the early universe, this baryonic matter existed primarily as a diffuse gas of hydrogen and helium atoms. But as the universe continued to expand and cool, this gas began to respond to the gravitational pull of the dark matter structures that were forming around it. The interplay between dark matter and ordinary matter during this period was crucial for the future evolution of the cosmos. Dark matter provided the gravitational framework, but it was ordinary matter that would eventually light up as stars and create the complex chemistry necessary for life. Without dark matter, the universe would have remained a thin, uniform soup of hydrogen and helium gas, never developing the dense concentrations of matter needed for star formation. Without ordinary matter, the universe would have been a dark network of invisible gravitational scaffolding, forever hidden from view. As millions of years passed, the gravitational influence of dark matter continued to shape the distribution of ordinary matter. Gas began to flow along the dark matter filaments, like water flowing through invisible channels in space. At the intersections of these filaments, where multiple streams of matter converged, the density began to build toward the critical threshold needed for the next phase of cosmic evolution. This process was not uniform across the universe. Some regions, blessed with slightly higher initial densities, developed more quickly than others. The first dark matter halos to reach sufficient mass began to attract substantial amounts of ordinary matter, setting the stage for the formation of the very first stars. These primordial stellar nurseries would eventually become the sites where hydrogen and helium gas would collapse under its own gravity, heat up to millions of degrees, and ignite the nuclear fusion reactions that would light up the cosmos for the first time since the cosmic microwave background had faded into darkness. The formation of these early dark matter structures also had profound implications for the thermal evolution of the universe. As ordinary matter fell into the gravitational wells created by dark matter, it was compressed and heated. This process converted gravitational potential energy into thermal energy, warming the gas and making it easier to detect. At the same time, the increasing density of matter in these regions made it more likely that the first stars would form, beginning the process that would eventually enrich the universe with heavier elements and create the conditions necessary for the formation of planets and life. The Dark Ages were thus anything but stagnant. While the universe may have appeared dark and empty to our eyes, it was actually undergoing a fundamental transformation that would determine its character for billions of years to come. The invisible hand of dark matter was sculpting the cosmic landscape, creating the framework upon which all future structures would be built. This period also marked the beginning of what cosmologists call hierarchical structure formation, the process by which small structures merge to form larger ones, which in turn merge to form even larger structures. The smallest dark matter halos formed first, followed by progressively larger systems as gravity continued its work of assembling matter into ever more massive concentrations. The end of the Dark Ages would come dramatically, when the first stars finally ignited and began to flood the universe with light and energy. But that moment was still hundreds of millions of years in the future. For now, the cosmos remained a patient construction site, with dark matter laying the foundation for all the wonders that were yet to come. As the cosmic stage is set with dark matter scaffolding and the fundamental forces established, we stand at the threshold of one of the universe's most profound transformations. For nearly 1,000,000 years, the cosmos has been shrouded in darkness, its fierce birth energy spent, its matter cooling and organizing in ways that will soon ignite the first beacons of light since the primordial fireball itself. The universe at this moment is a study in contrasts. While invisible dark matter has been quietly weaving the cosmic web that will define galactic architecture for eons to come, ordinary matter languishes in a state of cold, patient waiting. Hydrogen and helium atoms drift through space at temperatures barely above absolute zero, gathering in the gravitational wells carved out by their invisible dark matter companions. These are the dark ages of the cosmos, and they're about to end in the most spectacular fashion imaginable. The first stars that will soon ignite are unlike anything we see in our modern universe. These primordial giants, known to astronomers as population 3 stars, are monsters of unprecedented scale and fury. With masses reaching hundreds of times that of our Sun, they burn with an intensity that defies comprehension. Their cores reach temperatures of over 1,000,000,000 degrees Celsius, hot enough to forge the first heavy elements in the universe through nuclear fusion processes that our Sun could never achieve. But before these stellar furnaces can begin their cosmic alchemy, the raw materials must first overcome a fundamental challenge. The hydrogen and helium atoms floating in the early universe are electrically neutral, making them nearly invisible to electromagnetic radiation. This neutrality creates a problem. Without a way to efficiently radiate away excess energy, gas clouds cannot cool sufficiently to collapse under their own gravity. It's a cosmic catch-22 that threatens to keep the universe dark forever. The solution comes from an unexpected source, the very atoms themselves. When hydrogen atoms collide at just the right energies, they can form hydrogen molecules, H2. These molecular bonds create new pathways for energy to escape through rotational and vibrational transitions. It's a subtle process, almost insignificant by earthly standards. But in the pristine environment of the early universe, it becomes the key that unlocks stellar formation. As gas clouds begin to collapse, they fragment into smaller and smaller pieces, each piece growing denser and hotter as gravity works its inexorable pull. The process is not gentle. Computer simulations reveal that these first stellar nurseries are chaotic environments where gas streams collide at supersonic speeds, creating shockwaves that heat the material to thousands of degrees. In this cosmic furnace, the first protostars begin to form. The birth of a population 3 star is a violent affair that would make our sun's formation look positively serene. As the protostar's core temperature climbs toward 10 million degrees Celsius, nuclear fusion suddenly ignites in an explosive burst that sends shockwaves rippling through space. The star's outer layers are blasted away in a stellar tantrum that can be seen across millions of light years. But the core survives, settling into a rhythm of nuclear burning that will sustain it for perhaps only a few million years. These first stars are fundamentally different from modern stars in ways that extend far beyond their enormous size. They are composed almost entirely of hydrogen and helium, the primordial elements forged in the Big Bang's first 20 minutes. This pure composition has profound consequences for how they live and die. Without heavier elements to help transport energy from their cores, population 3 stars must burn hotter and faster than their metal-enriched descendants. They are cosmic sprinters rather than marathon runners. The nuclear processes occurring within these stellar giants are more complex than anything happening in our Sun. While our star primarily converts hydrogen into helium through the proton-proton chain reaction, population 3 stars have access to more exotic fusion pathways. In their billion-degree cores, helium nuclei can collide with such violence that they stick together, forming carbon through the triple alpha process. This carbon then serves as a catalyst for further fusion reactions, enabling the production of oxygen, neon, magnesium, and silicon. As these massive stars age, their cores become cosmic onions, with layers of different elements burning at different temperatures and pressures. The outermost layer continues to burn hydrogen into helium, while deeper layers fuse helium into carbon, carbon into oxygen, and so on, all the way up to iron. This element, with 26 protons in its nucleus, represents a cosmic dead end. Iron cannot be fused to release energy. Instead, any further nuclear reactions actually consume energy, spelling doom for the star. The end comes suddenly and catastrophically. When a population 3 star's core fills with iron, nuclear fusion ceases almost instantly. Without the outward pressure of fusion energy to balance gravity's inward pull, the core collapses in less than a second, crushing matter to densities that rival atomic nuclei themselves. The collapse rebounds in a supernova explosion so violent that it can outshine an entire galaxy for weeks. These primordial supernovae are cosmic game changers. They scatter the heavy elements forged in stellar cores across hundreds of light years of space, seeding the universe with carbon, oxygen, silicon, and iron for the first time. These elements will become the building blocks of planets, atmospheres, and eventually life itself. In a very real sense, we are made of ancient starlight, our bodies constructed from atoms that were forged in the nuclear furnaces of stars that died billions of years before our sun was born. But the influence of population 3 stars extends beyond mere element production. Their intense ultraviolet radiation begins to ionize the hydrogen atoms in surrounding space, creating vast bubbles of hot, glowing gas. This process, known as reionization, gradually transforms the universe from a cold, neutral medium back into the ionized plasma it was during its first few 100,000 years. The cosmic dark ages are ending, and a new era of light and energy is beginning. The formation of the first stars also marks the beginning of cosmic feedback processes that will shape galaxy formation for billions of years to come. The energy released by these stellar giants creates powerful winds that can blow gas out of small dark matter halos, preventing further star formation. This feedback helps explain why small galaxies today contain far fewer stars than astronomers might otherwise expect based on their dark matter content alone. As the first generation of stars lives and dies, they paved the way for a second generation of stellar formation. These population 2 stars, while still massive by modern standards, are enriched with the heavy elements scattered by their predecessors' death throes. This metal enrichment fundamentally changes how stars form and evolve, enabling more efficient cooling and allowing for the formation of smaller, longer-lived stars. The transition from population 3 to population 2 star formation represents one of the most important phase changes in cosmic history. It marks the universe's transformation from a simple, two-element system to a complex, chemically diverse environment capable of supporting the rich tapestry of astronomical phenomena we observe today. Rocky planets become possible for the first time, as silicon and iron provide the raw materials for solid world formation. The first galaxies begin to emerge as dark matter halos grow massive enough to retain their gas despite the energetic feedback from stellar explosions. These primordial galaxies are small, irregular collections of stars and gas, bearing little resemblance to the majestic spiral and elliptical galaxies we see in the modern universe. They are cosmic laboratories where the processes of star formation, chemical enrichment, and galactic evolution are worked out through trial and error over hundreds of millions of years. The supermassive black holes that will eventually anchor galaxy centers also begin to form during this epoch, though their origins remain one of astronomy's greatest mysteries. Some may grow from the remnants of the most massive population 3 stars, while others might form through the direct collapse of primordial gas clouds. Regardless of their formation mechanism, these black holes will play crucial roles in regulating star formation and shaping galactic evolution throughout cosmic history. As we stand at this pivotal moment in cosmic history, we witness the universe's transformation from a dark, simple place to a bright, complex cosmos teeming with energy and activity. The first stars have broken the cosmic silence, their nuclear fires blazing across the void like beacons of hope in an endless night. They are the universe's first act of creation since the Big Bang itself, the moment when gravity finally overcame the expansion and cooling that had dominated the first million years of cosmic evolution. The legacy of these first stars extends far beyond their immediate environment. Every atom in your body heavier than hydrogen and helium was forged in the nuclear furnace of an ancient star, or created in the violent explosion that marked its death. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar cores that burned billions of years ago. We are not just observers of the cosmic story. We are active participants, constructed from the very elements that these first stars bequeathed to the universe. The era of first light represents more than just the end of the cosmic dark ages. It marks the beginning of the universe's long journey toward complexity, diversity, and ultimately, consciousness itself. From these humble beginnings, simple atoms collapsing under gravity's pull, will emerge the rich ecosystem of galaxies, planets, and life that characterizes our modern cosmos. The first stars are the universe's first steps toward awakening, the moment when it begins to know itself through the eyes of the conscious beings it will eventually create. As we reach the climactic understanding of gravity's cosmic architecture, we must contemplate what would happen if this fundamental force, the sculptor of galaxies, the heartbeat of stars, the very foundation upon which complexity stands, simply vanished. The implications stretch far beyond our Earth, beyond our solar system, beyond even our galaxy, reaching into the deepest structures of space-time itself. Without gravity, the intricate cosmic web we've traced through 13.8 billion years of evolution would unravel in an instant. The dark matter scaffolding that guided the formation of the first stars would lose its binding power. Those primordial overdensities that grew from quantum fluctuations during inflation would disperse like smoke in a cosmic wind. The delicate balance between expansion and gravitational attraction that allowed structure to form would tip catastrophically toward chaos. Consider the fate of galaxies themselves. These magnificent spiral arms, these elliptical giants, these irregular clusters, all held together by gravity's invisible hand, would fly apart as their constituent stars scatter in every direction. The Milky Way's beautiful spiral structure, carved by density waves and gravitational resonances, would dissolve as 200 billion stars suddenly follow straight-line trajectories through space. Our neighbouring Andromeda galaxy, currently racing toward us for a collision in 5 billion years, would instead see its own stars dispersing into the void. But the dissolution would cascade deeper still. Within each scattering star, the nuclear furnaces that have burned for billions of years would face immediate crisis. The gravitational pressure that confines stellar cores, enabling the quantum tunneling that allows hydrogen to fuse into helium, despite electromagnetic repulsion, would vanish. Without this crushing embrace, nuclear fusion would sputter and die. The stars would begin to cool, their light fading as the cosmic beacons that have illuminated the universe for eons go dark one by one. The death of stellar fusion would have profound consequences for the chemical evolution of the cosmos. Those massive stars that forge elements heavier than iron in their cores, then distribute them through supernova explosions triggered by gravitational collapse, would no longer enrich the interstellar medium. The cosmic recycling program that has steadily increased the metallicity of the universe, enabling the formation of rocky planets and the chemistry of life, would grind to a halt. Planetary systems would face immediate disintegration. Earth would hurtle away from the sun in a straight line, carrying with it the moon, which would itself drift away from our planet. The delicate orbital mechanics that maintain stable climate patterns, that create tidal forces, that govern the complex dance of celestial bodies, would collapse into simple, inertial motion. Every planet, every asteroid, every comet would follow its own trajectory through space, never again to feel the gentle tug that keeps solar systems coherent. Black holes, those ultimate manifestations of gravity's power, would face a paradoxical fate. The event horizons that define them exist only because space-time curvature becomes so extreme that not even light can escape. Without gravity to curve space-time, these cosmic monsters would lose their defining characteristic. The matter trapped within would suddenly find itself free to escape, though the energy required for this liberation remains unclear in our hypothetical scenario. The cosmic microwave background radiation, that ancient light from when the universe first became transparent, carries within its subtle temperature variations the imprint of gravitational physics. The baryon acoustic oscillations that created peaks and troughs in matter density depended on the interplay between photon pressure and gravitational attraction. Without gravity, these patterns would never have formed, and the large-scale structure of the universe would remain forever smooth and featureless. Dark matter, which comprises 85% of all matter in the universe, would lose its primary means of interaction. These weakly interacting massive particles reveal themselves only through their gravitational effects, the way they curve space-time, the way they shepherd ordinary matter into cosmic web filaments, the way they form invisible halos around galaxies. Without gravity, dark matter would become not just invisible, but effectively non-existent in terms of its cosmic influence. The expansion of the universe itself would face dramatic changes. While dark energy appears to drive accelerated expansion, gravity provides the counterbalancing force that has shaped the universe's expansion history. In the early universe, when matter dominated over dark energy, gravity slowed the expansion rate. Without this cosmic break, the universe might have expanded so rapidly that no structures could ever have formed. leaving only an eternally thinning soup of particles. Even the fundamental nature of spacetime would be called into question. Einstein's general relativity tells us that gravity is not a force in the traditional sense, but rather the curvature of spacetime itself. Matter and energy tell spacetime how to curve, and curved spacetime tells matter how to move. Without gravity, spacetime would lose its dynamic character, becoming flat and static, a fixed stage rather than an active participant in cosmic drama. The implications extend to time itself. Gravitational time dilation, confirmed by countless experiments, shows that time passes differently in gravitational fields. GPS satellites must account for this effect to maintain accuracy. Near massive objects, time slows relative to distant observers. Without gravity, this relativistic effect would vanish, leaving time uniform throughout the cosmos. The rich temporal structure that gravity creates, from the extreme time dilation near black holes to the subtle effects at Earth's surface, would flatten into monotonous universality. Remarkably, the universe's capacity for complexity would collapse entirely. Gravity enables the hierarchical structure formation that characterizes our cosmos. Quantum fluctuations grow into overdensities. Overdensities become dark matter halos. Halos attract gas that forms stars. Stars forge heavy elements and explode to seed new star formation. Stellar systems develop planets, and on at least one planet, complex chemistry gives rise to life and consciousness. Without gravity, this magnificent cascade of increasing complexity would never begin. The cosmic web, that grand architecture of filaments, nodes, and voids that spans billions of light years, would never form. Dark matter would remain uniformly distributed. Ordinary matter would follow suit, and the universe would maintain the smooth density it possessed shortly after inflation. No galaxies, no stars, no planets, no chemistry, no biology, no observers to contemplate the cosmos. Perhaps most profoundly, the universe would lose its capacity for memory. Gravitational systems encode their histories in their structures. The spiral arms of galaxies record density waves. Planetary orbits preserve angular momentum from formation disks. Tidal forces sculpt moons and rings. Without gravity, these records would vanish, leaving no trace of cosmic evolution. In contemplating a universe without gravity, we see revealed just how essential this force is to everything we know and value. It is not merely one force among four, but the cosmic architect that enables all complexity, all structure, all life. Gravity transforms simple initial conditions into rich, hierarchical systems. It builds the stage upon which the cosmic drama unfolds and writes the script that governs the performance. The universe without gravity would be a place of eternal, featureless expansion. Particles moving in straight lines through flat spacetime, never gathering into anything more complex than the elementary constituents of matter that emerge from the Big Bang's first moments. It would be a cosmos of maximum entropy from the start, incapable of the decreasing entropy gradients that allow for structure, information, and life. In recognizing gravity's cosmic significance, we gain profound appreciation for the universe we inhabit, a cosmos where this fundamental force has spent nearly 14 billion years building magnificent complexity from quantum simplicity, creating the very possibility of understanding itself through the minds it has ultimately enabled to emerge. Without gravity, the very essence of what makes our universe meaningful would vanish. The delicate dance between matter and energy that has played out over billions of years would come to an abrupt and catastrophic end. But understanding what would happen if gravity disappeared isn't just about imagining destruction. It's about appreciating the profound role this fundamental force plays in literally everything we see, touch, and experience. Consider for a moment the exquisite precision required for our existence. If gravity were even slightly weaker, the universe would be nothing more than an ever-thinning soup of hydrogen gas, unable to condense into the complex structures that define our cosmos. If it were marginally stronger, everything would collapse into black holes or violent, short-lived stars, leaving no room for planets, life, or the intricate chemistry that makes biology possible. This fine-tuning extends far beyond the obvious. Gravity doesn't just hold planets in orbit or keep our feet on the ground, it governs the very rate at which time passes. Einstein's revolutionary insights showed us that gravity and time are inextricably linked. The stronger the gravitational field, the slower time moves relative to regions of weaker gravity. Without gravity, this fundamental relationship between space and time would cease to exist, and the fabric of space-time itself would lose all meaning. The absence of gravity would also eliminate one of the universe's most important regulatory mechanisms. Throughout cosmic history, gravity has acted as nature's sculptor, taking the primordial quantum fluctuations that emerged during inflation and transforming them into the magnificent structures we observe today. Those tiny variations in density, stretched to cosmic scales during the universe's first fraction of a second, provided the seeds that gravity could work with. Over millions and billions of years, gravity pulled matter together into increasingly complex arrangements, first dark matter halos, then gas clouds, then stars, then galaxies, then clusters and superclusters spanning hundreds of millions of light years. Without gravity's patient work, none of this architectural complexity could exist. The universe would remain forever locked in the smooth, featureless state it possessed moments after the Big Bang. There would be no hierarchy of structure, no evolution from simple to complex, no pathway from the primordial plasma to the rich tapestry of cosmic organization we see today. Perhaps most profoundly, the loss of gravity would represent the end of causality as we understand it. Gravity doesn't just attract matter, it provides the mechanism by which events in one part of the universe can influence events in another. Gravitational waves, ripples in space-time itself, carry information across vast distances at the speed of light. These waves allow the universe to maintain a kind of cosmic coherence, ensuring that the laws of physics operate consistently throughout space and time. The nuclear processes that power stars and create the heavy elements essential for life depend critically on gravity's compressive force. Without the immense pressure created by a star's gravitational collapse, hydrogen nuclei could never overcome their electromagnetic repulsion to fuse into helium. The quantum tunneling that allows nuclear fusion to occur at temperatures far below what classical physics would predict only works because gravity provides the necessary conditions. Remove gravity, and the universe becomes chemically sterile, forever limited to the lightest elements created in the first few minutes after the Big Bang. Even more subtle is gravity's role in enabling the arrow of time itself. While the fundamental forces of physics are largely time-symmetric, gravity provides the mechanism by which the universe can evolve from ordered to disordered states. The formation of structure under gravity's influence creates the thermodynamic gradients that allow energy to flow from hot to cold, enabling the processes that drive complexity and ultimately life itself. The quantum vacuum, that seething sea of virtual particles that underlies all of reality, would also be profoundly affected. Gravity couples to all forms of energy, including the zero-point fluctuations of quantum fields. Without gravity's organizing influence, these quantum fluctuations would remain forever random and uncorrelated, unable to seed the formation of structure or provide the subtle variations that break the perfect symmetry of empty space. Consider, too, the role gravity plays in information processing and the emergence of consciousness. The complex neural networks in our brains, the intricate molecular machinery of life, The delicate chemical processes that enable metabolism and reproduction, all of these depend on gravity's ability to create stable, long-lived structures. Without gravity, matter would remain forever dispersed and disconnected, unable to form the concentrated arrangements necessary for information storage and processing. The absence of gravity would also eliminate the possibility of geological processes that have shaped planetary environments and created the conditions for life. Plate tectonics, volcanic activity, the formation of atmospheres and oceans, the cycling of elements between different chemical reservoirs. All of these processes depend fundamentally on gravity's ability to segregate materials by density and drive large-scale flows of matter and energy. Even the very concept of location would lose its meaning in a universe without gravity. With no gravitational wells to define special places, no centers of mass around which other objects can orbit, space would become perfectly homogeneous and isotropic. There would be no here or there, no reference points by which to navigate or organize experience. The rich geography of the cosmos, with its galaxies and clusters and vast cosmic web of filaments and voids, would be replaced by perfect, featureless uniformity. The loss of gravity would represent not just the end of structure, but the end of time itself as a meaningful concept. Without the irreversible processes of gravitational collapse and structure formation, without the thermodynamic flows that create entropy gradients, the universe would exist in a timeless equilibrium. There would be no past to remember, no future to anticipate, no evolution or change or development of any kind. In contemplating a universe without gravity, we come to appreciate that this force is not merely one among many physical phenomena, but the very foundation upon which all complexity, all meaning, all possibility rests. Gravity is the architect of reality itself, the sculptor of space and time, the enabler of causality and change and growth. Without it, the universe would be not just empty, but empty of potential, a vast, changeless void where nothing ever was, is, or could be. The universe we inhabit today is the result of an extraordinary cosmic journey spanning 13.8 billion years. But perhaps the most remarkable aspect of this story is not just what happened, but what would happen if one of its most fundamental ingredients suddenly vanished. We've explored the birth of matter from pure energy, the formation of the first atoms, and the emergence of cosmic structure. We've witnessed the dance of dark matter and dark energy, the nuclear fires that forge elements in stellar cores, and the delicate balance of forces that allows complexity to flourish. But gravity, that seemingly gentle force that keeps your feet planted on the ground, is far more than just what prevents you from floating away. Gravity is the cosmic architect. It is the force that transforms quantum fluctuations into galactic superclusters, that ignites the nuclear furnaces of stars, and that maintains the intricate orbital mechanics, allowing planets to exist in stable configurations for billions of years. Without gravity, there would be no stars to cook the heavy elements essential for rocky planets. Without gravity, there would be no planets to serve as stable platforms for the chemistry of life. Without gravity, there would be no galaxies to organize matter into the cosmic web we observe today. But gravity's influence extends far beyond these obvious structural roles. In Einstein's universe, gravity is not merely a force, but the very curvature of space-time itself. It is gravity that gives meaning to the flow of time, creating the causal relationships that allow events to unfold in sequence. The gentle warping of space-time around massive objects doesn't just guide the motion of planets and stars, it orchestrates the fundamental rhythm of existence itself. Consider what this means for the emergence of consciousness. The atoms in your brain were forged in the cores of ancient stars, stars that could only exist because gravity compressed hydrogen and helium to the extreme temperatures and pressures necessary for nuclear fusion. The carbon, oxygen, and nitrogen that form the backbone of your DNA were scattered across space by stellar explosions, explosions that occurred because gravity could no longer balance the outward pressure of nuclear fire in dying stars. These elements then gathered into new solar systems, again under gravity's patient influence, eventually forming rocky worlds where the complex chemistry of life could unfold. Even the process of biological evolution depends fundamentally on gravity. It provides the stable, long-term environments necessary for the slow accumulation of genetic changes over millions of years. It maintains the atmospheric pressure that allows liquid water to exist on planetary surfaces. It drives the geological processes that recycle nutrients and maintain the chemical gradients essential for metabolism. In our exploration of cosmic history, we've seen how gravity has been the constant companion of complexity. From the moment when quantum fluctuations were stretched by cosmic inflation to become the seeds of galaxies, gravity has been patiently gathering matter, concentrating energy, and creating the conditions for ever more intricate structures to emerge. The spiral arms of galaxies, the hierarchical clustering of galactic superclusters, the formation of planetary systems, all of these represent gravity's ongoing project of organization and complexity. Yet perhaps most profoundly, gravity enables the universe to know itself. By creating the conditions for stars, planets, and ultimately life, gravity has made possible the emergence of conscious observers capable of contemplating their cosmic origins. The very fact that we can trace the universe's history from the Big Bang to the present day is a testament to gravity's role in creating structures complex enough to support intelligence. The universe without gravity would not simply be chaotic, it would be profoundly empty. There would be no mechanism for matter to organize itself, no way for energy to concentrate into the dense configurations necessary for nuclear fusion, no process by which simple hydrogen could transform into the rich periodic table of elements that makes chemistry possible. The quantum vacuum fluctuations that we now see imprinted on the cosmic microwave background would remain forever microscopic, never growing into the cosmic web of dark matter filaments that serves as the scaffold for all visible structure. In the end, gravity reveals itself to be far more than one of four fundamental forces. It is the enabler of existence itself, the cosmic force that transforms a universe of uniform simplicity into a cosmos of stunning complexity and beauty. From the largest galactic superclusters to the smallest details of planetary geology, from the nuclear processes that power stars to the biological processes that power life, gravity is the invisible hand that makes it all possible. Without gravity, the universe would be not just empty, but meaningless, a featureless expanse where nothing interesting could ever happen, where no stories could unfold, where no consciousness could arise to ponder the mystery of existence. Gravity, in its quiet persistence, is nothing less than the author of cosmic significance itself.